This lecture will cover the CFA Level I reading on statistical concepts and market returns. Statistics. Descriptive statistics describe the properties of a large data set. For example, a classic descriptive statistic would be the mean. If you want to observe a large portfolio with say 100 stocks, and you want to say what is the average return of a stock in this portfolio, that would be an example of a descriptive statistic. Inferential statistics use a sample from a population to make probabilistic statements about the characteristics of a population. Now here again, let's say that you are observing all 700 stocks in the Karachi Stock Exchange, and you don't have time to study all 700, so you might pick out a sample of 50 stocks, and so this is your sample, and with this sample of 50 stocks you now look at the average return of the sample, and based on the average return of the sample you make an inference about the average return of all 700 stocks. So this would be an example of inferential statistics, where you are taking statistics related to the sample and using that to make an inference about the overall population. As you might have gathered by now, a population is a complete set of outcomes. So in my example here, the 700 stocks in the Karachi Stock Exchange would be a population, and the 50 stocks that I pull out at random would be my sample. So a sample is a subset drawn from a population. Some statistical terms. A parameter describes a characteristic of a population. So continuing with my example, if I take all 700 stocks in the Karachi Stock Exchange and find their average return, the average return for the whole population would be called a parameter. A sample statistic describes a characteristic of a sample. Now from this I draw a sample of 50 shares, and if I now find the average return of the 50 shares in the sample, that would be called a sample statistic. A relative frequency distribution shows the percentage of a distribution's outcome in each interval. A cumulative frequency distribution shows the percentage of observations less than the upper bound of each interval, and we will see these two terms explained in more detail shortly. Measurement scales. From an exam perspective, you just need to know these terms. A nominal scale is one where only the names make sense. For example, if we have three different funds, a value fund, a growth fund, and an Islamic fund, these three funds are not, one is not necessarily better than the other, so there is no scaling or rating involved here. The three funds are just distinguished based on three different names, and they will each have their own characteristics. So the core point is, with a nominal distribution, only the names make sense. Second comes an ordinal distribution, where an order makes sense. So if, for example, you are evaluating portfolios, or you are evaluating let's say portfolio managers, and the best portfolio managers who have performed extremely well in the last year get a 3-star rating. Those who have performed below that get a 2-star rating, and the ones at the bottom end get only a 1-star rating. So this would be a ordinal scale, where the order does make sense, but it is not clear that if the 3-star is better than 2-star, then it's not necessary that 2-star is better than 1-star by the same amount. So all we are saying is 3-star is better than 2-star, which is better than 1-star. With interval scales, the interval does make sense. So a classic example of an interval scale is temperature. So 40 degrees Fahrenheit is 10 degrees centigrade greater than 30, and 30 would be, or 10 degrees Fahrenheit, and 30 would be 10 degrees Fahrenheit greater than 20. So here the interval makes sense. And finally, we have a ratio scale where ratios also make sense. And the important part of a ratio scale is that there is an absolute zero. Note that 0 degrees Fahrenheit up here so 0 degrees Fahrenheit does not mean that there is no temperature. But when you come to a ratio scale, and let's say we are talking about profits, so if profit is equal to 0, that means there is no profit, and hence this would, we can easily work with ratios. So if profits go from 100 to 200, the ratio is that profits double. Similarly, if we go from 200 to 400, then here again profits double. So core point with ratio scales is that ratios make sense, and also that there is an absolute zero. So just make sure that you know a couple of lines on each one of these scales, and that you can relate to these with some simple examples. A frequency distribution is a tabular presentation of statistical data that aids the analysis of large datasets. Frequency distributions summarize statistical data by assigning it to specified groups or intervals. 3 steps are required to construct a frequency distribution. First, you define the intervals. Second, tally the observations, assign observations to intervals. And third, count the observations in each interval. So let's look at a simple example now. Say you have 100 students who take an exam, and their marks range from 45 to 65. The first thing that you do is tally the marks, or the first thing actually you do is create your categories. So 45 to 50, 51 to 55, 56 to 60, and 61 to 65. So these are your intervals basically. Then you observe, or you tally, and you see how many students got marks in this interval, 45 to 50. So we see that 25 students are in the 45 to 50 range, 35 are in the 51 to 55 range, 29 in the 56 to 60 range, and 11 in the 61 to 65 range. So that is your frequency. Cumulative frequency basically is going to add up all the frequencies up to a given point. So in the range 45 to 50, we have a cumulative frequency of 25. When we say cumulative frequency for 51 to 55, what we really mean is how many students got 55 and below. So that would simply be 25 plus 35, which is 60. This cumulative figure of 89 means how many students got 60 or below. So you simply add the 29 and you get 89. And finally, if 65 was the highest mark, then how many students got 65 or below? And the answer is 100, because that was the total number of students that we had. So that's cumulative frequency. Relative frequency is quite similar. It is the percentage of total observations falling within each interval. So the total observations are 100. If in this first interval of 45 to 50, you have 25 students, then the percentage is 0.25 or 25%, and then 35 out of 100 would be 0.35, and so on. So that's relative frequency. Cumulative frequency is like cumulative relative frequency is simply requires us to add up these numbers. So I'll first read the definition. Cumulative relative frequency is the sum of the relative frequencies up to and including the given interval. So let's say our interval is 51 to 60. So the relative frequency up to and including this interval would be 0.25 plus 0.35, which is 0.6, and so on. So the cumulative relative frequency for 51 to 60 would be everything up to and including 60, which would be 0.25 plus 0.35 plus 0.29, which is 0.8. And if 65 is the highest mark, then 1.0 or 100% of the students got 65 or below. Now let's look at some graphical representations. A histogram is the graphical equivalent of a frequency distribution. It is a bar chart of continuous data that has been grouped into a frequency distribution. The advantage of a histogram is that we can quickly see where most of the observations lie. For a histogram, on the y-axis we will plot the frequency. So given this sort of data, let's say that we plot 10, 20, 30 and 40, and on the x-axis we will put the different ranges or categories. So 45 to 50, 51 to 55, 56 to 60 and 61 to 65. Now 41 to 50, we have 25 students in this range, so 25 is about there. So we create a bar that has a height of 25. Then in the 51 to 55, the frequency is 35. So here we create a bar with a height of 35. 56 to 60 has a frequency of 29. So we find the 29 point and create a bar with a height of 29. And finally 61 to 65 is 11. So here we create a bar with a height of 11. So this is your histogram, and as you notice, the advantage of a histogram is that we can quickly see where most of the observations lie. So now let's talk about a frequency polygon. With a frequency polygon, we plot the midpoint of each interval on the horizontal axis and the absolute frequency for that interval on the vertical axis. Each point is then connected with a straight line. So the first thing we do is let's just come up with the midpoints. So the first midpoint for this interval is 47.5, and then the midpoint here is 53. The midpoint here is 58, and the midpoint here is 63. So on the x-axis we can plot the midpoints, which are 47.5, 53, 58 and 63. And on the y-axis we can plot the frequencies, which are, so like before, we'll just go with 10, 20, 30 and 40. So for the midpoint 47.5, we have a frequency of 25, so we come to the 25 point. For the second midpoint of 53, we have a frequency of 35, so we go up to about 35, which is this point, and then for the next range 58, or the midpoint 58, the frequency is 29, So 58 go up to about 29, so that's this point, and 63 11, so 63 go up to about 11, and then we simply connect these points. So like that, and that is our frequency polygon. Straightforward. Now let's look at measures of central tendency, population and sample means. So the most common measure of central tendency is a mean or average, and population and sample means have different symbols but are both basically arithmetic means. We've already talked about the distinction between population and sample, and I'll remind you of that example. Let's say our population is 700 stocks on the Karachi Stock Exchange, and out of this we might pull out a sample of 50. When we are talking about the mean return for all 700 shares, that's a population mean, and that's denoted by mu, and this is simply the average, so that's the summation sign. That's the return xi of every single stock. I is equal to 1 to 700 for all 700 stocks divided by n, which is 700 for my example. The sample mean is denoted by x bar, and here we have 50 stocks, so our sample mean would be the summation of I equals 1 to 50. xi is the return on each one of those 50 stocks divided by n, which is 50 for our sample. Arithmetic mean. So the arithmetic mean is the sum of the observation values divided by the number of observations. It is the most widely used measure of central tendency and is the only measure when the sum is the only measure where the sum of the deviations of each value from the mean is always 0. The formula for calculating the arithmetic mean of n values is this. So all you are doing is adding up all the values and dividing by n, which is the number of values. What does this mean? Sum of the deviations. All this means is if the mean is 50 and you have, let's say, 3 observations, 40, 50 and 60. So the mean is 50. The sum of the deviations is 0. So this means, what's the deviation here? We are 10 below the mean, so the deviation is minus 10. For 50 the deviation is 0, so plus 0, and for 60 the deviation is plus 10. So notice that the sum of the deviations is 0. Another measure is geometric mean. So this is also a measure of central tendency. Geometric mean is used to calculate period compound growth rates. So when you have time series data, which a classic example of time series data is the return on a stock over time. So let's say that you own shares of XYZ company and you owned this share over the last 3 years. In the first year that you owned it, you had a return of 10%. In the second, you had 20%, and in the third year, you had 15%. So how do we find the geometric mean here? And the answer is that the geometric mean or the period compound growth rate would be equal to 1 plus the return in the first year, which is 0.1, times 1 plus the return in the second year, which is 1 plus 0.2, into 1 plus 0.15, and then this is all raised to the power of 1 over n. N is 3 here, 3 years, and then you subtract 1. So that is how you calculate a geometric mean. Notice that with arithmetic mean, you simply add the numbers and divide by the number of observations. Here you multiply and then you use an exponent where you have 1 over n, n being the number of observations. If returns are constant over time, then geometric mean equals arithmetic mean. So if you take this simple example, if your return was 10%, 10%, and 10%, then your arithmetic mean would be 10%, and the geometric mean would also be 10%, which you can verify by plugging in 10%, 10%, and 10%. You will get a geometric mean of 10%. The arithmetic mean is obviously 10%. The greater the variability of returns over time, so for example, if your returns are 10%, 50%, and 2%, so this is high variability. If you have high variability, then the difference between the arithmetic mean and geometric mean becomes more. And I'd suggest you pause the video here and actually do this. So calculate the arithmetic mean and calculate the geometric mean, and you will notice that the two will diverge. So let's do another example for geometric mean. An investment account had returns of 15%, minus 9%, and 13% over the last 3 years. Let's calculate the time-weighted annual rate of return. So essentially we are calculating the geometric mean here. So let's look at let's just first put down the formula. So our geometric mean formula told us that we need to do 1 plus R1 into 1 plus R2 into 1 plus R3, and then we are to do 1 over n. N is 3 and minus 1. So let's plug in the numbers. So geometric mean is 1 plus R1, which is 0.15, into 1 plus R2, which is actually, so a minus 9% return means that you do 1 minus 0.09 into 1 plus R3. R3 is 13%, so you do 1 plus 0.13, and all this will be raised to the power of 1 over n. N is 3, so 1 over 3 minus 1, and basically what you get is, when you do this calculation, you will get 0.0575, which is equal to 5.75%. So what this is basically saying that over the 3 years, your annualized growth rate was 5.75%. So if you had an investment where you got 5.75%, 5.75%, and 5.75% over 3 years, the return or the amount of money that you have at the end is equal to what you would have if the return was 15%, minus 9%, and 13% over the 3 years. Now let's talk about the concept of the harmonic mean. The harmonic mean is used by investors to find the average cost of shares purchased over time. Take an example. Let's say that an investor spends $1,000 every month for 3 months to buy shares of XYZ company. In month 1, let's say that he bought shares for $8, and then in month 2, he bought the shares of XYZ for 9, and then in month 3, he paid $10 for each share. Now the question is, on average, how much did he buy a share for? And that answer is the harmonic mean. So let me just give you the formula for the harmonic mean and then apply it here. So the harmonic mean formula is n over 1 over x1 plus 1 over x2 and so on till 1 over xn. Now n is the number of entries, so in our example n is 3. x1 is x1, x2, x3 are the items of which you are finding the harmonic mean. So for our example, let's just plug in. So n is 3 divided by 1 over 8 plus 1 over 9 plus 1 over 10, and this will give you an answer of 8.926. So what this says, that on average the investor paid 8.926 per share. Another way of looking at this, which is very straightforward, how much did an investor pay on average? He paid what's the total amount that he paid? The total amount that he paid was 3,000, because he spent 3,000 over 3 months. And then over the total number of shares that he bought. In month 1, how many shares did he buy? He spent 1,000. Each share was worth 8, so he bought 1,000 over 8. In month 2, he bought 1,000 divided by 9, and in month 3 he bought 1,000 divided by 10. So notice that basic mathematics, so the thousands cancel out, and effectively we have the same formula that we just used, and that's the intuition behind the harmonic mean. So again, bottom line is, the concept behind harmonic mean is that this is the mean that is used to determine how much an investor paid on average for shares, where he is buying the shares and spending an equal amount of money every time. So let's compare the three means that we've talked about. If observations in a data set have the same value, then arithmetic mean, geometric mean, and harmonic mean will all be the same. And you can just prove this to yourself. If you have 3 observations which are all 10%, the arithmetic mean is obviously 10%. Calculate the geometric mean, that will be 10%. Calculate the harmonic mean, and that will also be 10%. However, if observations in a data set have different values, so if you have 10%, 15%, and 2%, then there will be a difference between arithmetic mean, geometric mean, and harmonic mean. And specifically, the arithmetic mean will be greater than the geometric mean, which will be greater than the harmonic mean. The final kind of mean that we will talk about now is the weighted average, or the weighted mean. So here we basically, so this is where a mean in which different observations are given different proportional influence on the mean. So let's understand this through an example. Say you have a portfolio at the beginning of the year, which is cash 4 million, bonds 6 million, and equities 10 million. And the return on cash over the year is 5%. Then on bonds you got 7%, and on equities you got a return of 12%. If you are to calculate your average return for the year, it would not be appropriate to simply take the mean of 12, 5, and 7, because most of your money was in equities, or 50% was in equities. So clearly, equity, the return of 12% needs to be more heavily weighted than, say, the 5% return of cash. So essentially you take each one of the returns, 5%, 7%, and 12%, and you weight each one of these based on the percentage of that of that asset in the portfolio. So cash 5% return, what's the weightage? It is 4 divided by 20. 4 million cash divided by 20 million, which is the total portfolio. Bonds would be 6 million divided by 20, and equities is 10 million divided by 20. And the way you calculate the weighted mean is multiply the return by the weight. So you multiply these out, and the numbers that you will get are 1%, 2.1%, and 6%. And you add all these up and you get 9.1%. So your weighted average return is 9.1%. Okay, another measure of central tendency is the median. The median is simply the midpoint of a data set, where half your data is above and half your data is below. This is once you have ordered or arranged the data. So with an odd number of observations such as this, first thing you do is arrange from low to high, 2, 5, 7, 11, 14, and then the median will simply be the middle number. With an even number of observations, median is the average of the middle two observations. So here the middle two observations are 9 and 10. So the median would simply be the average of 9 and 10, which is 9.5. Notice that the median is less affected by extreme values than the mean. So if you just had an outlier here that was 2000, that would not affect the median, but obviously it would have a huge impact on the mean. And finally, you need to understand the mode. Mode is simply the value occurring most frequently in a data set. So in this example, 8 is the mode because it occurs most frequently. Data sets can have more than one mode. So for example, if we had 5 3 times in this observation, then we would say this is a bimodal distribution. In other words, it has two modes. A few comments here to keep in mind. To analyze data using the mean, median, and mode, we need to use the most appropriate measure of central tendency. And let's keep in mind the following points. The mean is most useful for predicting future results when there are no extreme values in the dataset. However, the impact of extreme values on the mean may be important and should be considered. For example, the impact of a stock market crash on average investment returns. The median may be more useful than the mean when there are extreme values in the data set, as it is not affected by extreme values. So when you are analyzing data and you feel that the extreme values are outliers and not important, then it is more appropriate to use the median. The mode is used when the most common item, characteristic, or value of a data set is required.